The next exercise we're going to look at is exercise 8.8, limiting sum of a series. Now we're going to look at two series. The first one here is 2 plus 4 plus 8 plus 16. Now we know that as the number of terms increases here, so as n increases, so does the sum of the series. It also increases. This is because r, in this case, is going from one term to the other. You're multiplying by 2, so r is 2. So when r is, in this case, as each term in the series gets bigger, if you consider the sum of the series, it will just get bigger and bigger. So we say, therefore, this series diverges or has an infinite sum as n increases. So as n, the number of terms, increases, the sum of this series gets bigger and bigger, so it diverges, and it has an infinite sum. Okay, so the value of the sum as n gets quite large will be quite large as well, the value of the sum. Now, if we look at this other series, 2 plus 1 plus a half plus a quarter, etc. Okay, so we've got 2 times a half is 1, 1 times a half is a half times a half is a quarter. So this has r equal to a half. Now I'm just going to do the sum of, let's say, sum Sn is, if you look at the formula, a 1 minus r to the n over 1 minus r. Remember, this is the formula we use if r, absolute value of r is less than 1. So in this case, I'm just going to do the sum of 10 terms, and I'm going to do the sum of 50 terms in this case. Okay, so the sum of 10 terms here would be a is 2. So here r is a half, a is 2. 1 minus r is a half to the power of 10 over 1 minus a half. So it's 1 minus a half is a half. Now 2 divided by a half is 4 times 1 minus 1 over a half. Sorry, 1 over 2, all to the power of 10. Now if we evaluate what that is, we get, now I've just done the sum to the first 10 terms and I get 3.99609. I was going to do the sum of 50 terms. I'm actually just going to do the sum of 20 terms first. I get 2, a is 2, 1 minus 1 half to the power of 20 over 1 minus a half, 1 minus r again, which is 4 times 1 minus a half to the power of 20. And if I just work that out on a calculator, I get 3.9999996, etc. So this looks like it is approaching 4. Okay, so the difference between these two series, they both start with 2, but one has r is 2. Now that series gets larger and larger, so the sum of the series diverges or has an infinite sum. But when r is, in this case, when r is a half or r is less than 1, it appears that the series, well, we can see that the series gets smaller and smaller. So the series converges, and so has, and we can see that the sum of, as n gets larger, the sum of the series approaches a certain value. So so the series converges, and so the sum of the series has a finite value, or a limiting, or it has a limiting value. Or we can say, or it's got a limiting sum. Okay, so this is called the limiting sum of a series. So sum to infinity equals a over 1 minus r. Now this sum to infinity formula will only applies if absolute value of r is less than 1. So the sum to infinity, So your sum will only converge, and there will only be a limiting sum if absolute value of r is less than 1. Okay, so here on your formula sheet where all your series stuff is, limiting sum of a geometric series, sum equals a over 1 minus r. We know that Sn equals a 1 minus r to the n over 1 minus r if r absolute value of r is less than 1. So if we just do an example, say if r is a half, let's do the sum of first 10 terms. It's a 1 minus a half to the power of 10 over 1 minus a half. Oh, sorry, over 1. I can leave it as 1 minus r, actually. Now, and I can look at S20. So that's a 1 minus a half to the power of 20 over 1 minus r. Now, if we look at the value of 1 half to the power of 10, that's 1 over 1024, which is quite small. It's actually almost 0. And if we look at the value of 1 half to the power of 20, that equals 1 half to the power of 20 is 1 over 1,048,576. So therefore, the half to the power of infinity, that would be approaching 0. So therefore, S sum to infinity is a 1 minus 0 over 1 minus r, which is a over 1 minus r. Because as n here gets very big, this value here is approaching 0. Okay, so that's just a quick proof. Example, does the following series have a limiting sum? Now, just because it's fractions, you don't assume that it does. So let's look at r, which is t2 divided by t1. So that's 1/8 divided by 5/8. So it's that over that, which is 1/8 times 8 over 5. So it's t2 divided by t1, which is 1/5. So therefore, because absolute value of r is less than 1, therefore the series has a limiting sum. Now, the series will only have a limiting sum if absolute value of r is less than 1. If the absolute value of r is greater than 1, then the series does not have a limiting sum. Okay, let's look at this one. So t2 over t1 is 36 over -6, which is -6. So therefore, the absolute value of r is greater than 1. So therefore, the series does not have a limiting sum. Remember, it has to be the absolute value of r is less than 1. Even though here r is less than 1, the absolute value of r is not less than 1. It's actually greater than 1. So if we do end up adding this series together, you'll find that as the number of terms goes on, the series will not approach a particular value. Okay? The value will keep changing. It won't approach a certain number. Okay, the next example is to find the limiting sum of this series here below. So here we can see that a is 2/5 and r is term 2 divided by term 1, which is 6 over 35 divided by 2/5, which is 6 over 35 times 5 over 2. We can do some simplification here, and we get 3/7. So therefore, the limiting sum of this series, so we know that absolute value of r is less than 1, therefore we can do sum to infinity is a over 1 minus r. So therefore that's a, which is 2/5, divided by this, just going back, sum to infinity is a over 1 minus r. A is 2/5 over 1 minus r is 3/7. So it's 2/5 divided by 4/7, which is 2/5 times 7 over 4. Just doing some simplifying here, and we get therefore that the sum to infinity is 7 over 10. So that's the limiting sum of that series. Okay, now for another example. Next example is to find the sum from n equals 3 to infinity of this particular, this is the nth term of the series, -4 times 2/3 to the n minus 1. Because we're starting with n is 3, we're going to substitute n is 3 here, and we'll get -4 times 2/3 to the power of 2 as the first term. And then the second term will be -4 times 2/3 to the power of, now if you've got n is 4 for the second term, you get 4 minus 1 is 3, so you get 2/3 to the power of 3, and so on. So therefore, if we want the sum of that series, we know that a, the first term, is negative 4 times 2/3 squared, which is negative 4 times 4 over 9, which is negative 16 over 9. Now r is term 2 divided by term 1. Now term 2 is negative 4 times 2/3 cubed over negative 4 times 2/3 squared. Negative 4's cancel, and 2/3 to the power of 3 over 2/3 to the power of 2 is just 2/3. So r is 2/3. Therefore, the sum to infinity is a over 1 minus r, which is a, which is negative 16 over 9 over 1 minus 2/3, which is negative 16 over 9 divided by 1/3, which is negative 16 over 9 times 3 over 1. And simplifying here, we get negative 16 over 3, which is negative 5 1/3. So the sum of this particular series there, from n is 3 to infinity, is negative 5 1/3. Examples. Now, a geometric series has a limiting sum of negative 6 2/5 and a first term of negative 8. Find its common ratio. So sum to infinity is a over 1 minus r. So the limiting sum is negative 6 2/5. The first term is negative 8, so a is negative 8 over 1 minus r. Now, changing this to an improper fraction, we've got negative 32 over 5 equals negative 8 over 1 minus r. I'm going to swap sides, or just multiply both sides by negative 1. I get 8 over 1 minus r equals 32 over 5. And now I can cross multiply, so 8 times 5 equals 32 times 1 minus r. So therefore 40 equals 32 minus, expanding, actually, no, 32 bracket, oh no, I'll expand, 32 minus 32r. So we've got 32 minus 32r, so therefore 32r, taking that to the other side, is 32 minus 40, so therefore 32r is negative 8. So r is negative 8 over 32, which is negative 1/4. So therefore the common ratio is negative 1/4, noticing that the absolute value of r is less than 1. Next example, the second term of a geometric series is 2 and the limiting sum is 9. So we know that geometric series Tn equals ar to the n minus 1. Now the second term is 2, so when n is 2, so t2 happens to be 2, which is ar to the 2 minus 1. In other words, 2 equals ar to the power of 1, or 2 is equal to ar. We know that the limiting sum, so sum to infinity, is a over 1 minus r. Now I'm going to call this equation 1. And we know that the limiting sum to infinity, is 9. So 9 equals a over 1 minus r. And that's equation 2. So we're going to solve simultaneously. So solving simultaneously. We know that we can either work out a or work out r first. I'm going to say that a, rearranging equation 1, a is 2 over r. We're going to sub into equation 2. So we get 9 equals 9 is equal to 2 over r over 1 minus r. So we get that 9 times 1 minus r equals 2 over r, multiplying by r again. So this is s to infinity equals a over 1 minus r. So we get that 9r bracket 1 minus r equals 2. The other thing we could have done here, this is 9 equals 2 over r. This 1 minus r ends up going down there next to it. But if you're not confident with that, you can write it as a over 1 minus r. Do your multiply here. Opposite of divide is times, and then you can opposite of divide by r is times by r again, and we get 9r minus 9r squared equals 2. And putting everything over to the right, we get 9r squared minus 9r plus 2 equals 0. So therefore r, using the, not sure if we can factorize that, we'll see. Just trying to factorize here. So 3r both minus. So we've got 9r squared minus 3r minus 6r plus 2, that works. So therefore 3r minus 2 equals 0, or 3r minus 1 equals 0. Therefore r is 2/3 or r is 1/3. So when r is 2/3, we're going to have to work out what a is. So subbing into equation 1, where or just sub into a equals 2 over r. So we get 2 divided by 2/3, which is 2 times 3 over 2, which is 3. So when a is 3, r is 2/3, and we can sub this also into a equals 2 over r, which is 2 divided by 1/3, which is 2 times 3, which is 6. So when a is 6, r is 1/3, or when a is 3, r is 2/3. And they're your two solutions to work out the values of a and r. Series x plus x over 4 plus x over 16 has a limiting sum of 7/8. Find x. Well, here we can see that a, first term, is x. R is t2 divided by t1, which is x over 4 divided by x, which is x over 4 times 1 on x, which is a quarter. So sum to infinity is a over 1 minus r. Sum to infinity is 7/8 equals x over 1 minus quarter. So that's 7/8 equals x over 3/4. So x divided by 3/4 is x times 4 over 3. And now solving, we get 7/8 times 3/4 times 3 over 4 equals x. And so therefore x is equal to 21 over 32. For what values of p will the limiting sum exist for this series? Now, we know that a limiting sum exists if absolute value of r is less than 1. In other words, that r lies between -1 and +1. So r is t2 over t1, which is -2p over 1, which is -2p. So therefore we've got -1 is less than -2p, which is less than -1. So to get p on its own, we have to divide by -2. Now when you divide by -2, you have to turn the inequality signs around. So it's -1 divided by -2, you have to turn the inequality sign around. -2p divided by -2, turning the inequality sign around again. 1 divided by -2. So therefore we get that p is greater than -1/2, but less than 1/2. The way we write that is like this. We never have the inequality signs that way. So p lies between -1/2 and +1/2. The question is to find the limiting sum when p equals 1/5. So here is our series, 1 minus 2p plus 4p squared minus etc. Now, if p is 1/5, our series becomes 1 minus 2/5 plus 4 over 25 minus etc. So therefore, replacing p with 1/5, we get 2 times 1/5 is 2/5. 1/5 squared is 1 over 25, so we get 4 times 1 on 25 is 4 on 25. Here we can see that a is 1, and that r is t2 divided by t1, which is -2/5 divided by 1, which is -2/5. So therefore, the sum to infinity is a over 1 minus r, which is 1 over 1 minus -2/5, which is 1 divided by 1 2/5, which is 7 over 5, which is 1 divided by 7 over 5, which is 5 over 7. Now that's the end of the examples. So if you could now please do exercise 8.8. Exercise 8.8, please do the following. Question 1, H and I. Question 2, G and J. Question 3B, 4J. Question 7, 14, 15, 16, 18 and 20.